In this video, we're going to look at how we take our exponential functions, those basic parent shapes, and apply our normal transformations to them. So if we look at this guy right here, f of x is equal to 2 raised to the x plus 2 minus 5, we want to make sure we understand what the basic function is here. So this guy is based off of 2 to the x. And if you remember his shape from the last video, this is that genie shape. Phenomenal cosmic power, but itty-bitty living space. Okay? He has a horizontal asymptote, but his domain is all real numbers. So he goes all the way left, all the way right. Now let's look inside this function to see what's going on. Well, up here, this is what's called inside that exponential, right? And when it's inside, remember, inside is a horizontal shift opposite of what you see. So that means here, we're going to be going to the left 2 units, and then whatever's outside the function, whatever's outside the exponential, that tells you a vertical shift, and you do exactly what you see. So I see the minus 5, which means I'm going to go vertically -5 or down 5 units. All right, so let's think about this. We know that the domain is going to be all real numbers. That's a given because it's exponential. My range was going to be from 0 to infinity, not including 0. And we had that horizontal asymptote at y equals 0. But we're going down 5. So let's go ahead and graph our horizontal asymptote by going down 5. And he's going to be right here. And then we also have that piece where we're going to the left 2. So this is not an asymptote, but I just want to make a little mark here so we know where we're supposed to be. I need to go to the left 2. So here's my y-axis to the left 2. So something kind of like that, where this is my new origin. So I'm going to mark this as, that's my new 0, 1, 2, 3, and so on. And let's see what we can get from this. Remember your key points for your exponential. I said there was an anchor point, a guy that we're going to have for all of these exponentials, and that's the key point 0, 1. Now, you don't plot 0, 1 from the original origin, but from our new one, because that's how we do our graphing, right? We shift, and we get a new point of reference. So from here, I'm going to plot the point 0, 1. And really, once you've got that point there, and you have your horizontal asymptote, you don't need to worry about the 2 and the 5. Don't worry about that. You want to focus on graphing this. How do I graph 2 to the x? In the last video, we talked about how that base tells you, as you move from left to right, what you're doing for each unit. That means you're going to be multiplying times 2. So right now, my distance here is 1. I want to multiply the distance times 2, so 1, 2. Then multiply that distance times 2, so 2, 3, it's going to be 4. Multiply that times 2, you get 8. So 4, 5, 6, 7, and 8. That's how you get your key points. Now go back to the left by dividing by 2. So half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is 1/2, 1/4, and so on like that. And so now we just connect the points, forming a nice, smooth, exponential graph. So this guy does blow up as you go from left to right, but he never goes completely vertical. There we go. Again, the key point is getting this guy right here, that new 0, 1. And again, just to make sure we understand how this is going, that is 1. That's 2 units, 4 units, and 8 units. You're multiplying times 2 every step you take going from left to right. If I did it again, I'd be up 16. So somewhere way up here, from down here is going to be 16 units. And then it's going to be times 2 again. So the next step would be 32 and 64 and so on. Okay? If the base had been 3, you would have still plotted 0, 1, no matter what the base is. And then if it had a base of 3 instead of 2, you'd multiply times 3. So you go from 1 to 3, 3 times 3 is 9, and then 27. And so you see that very quickly, we don't have room for all those points because the numbers get too big. Now let's take a look at this next one. In this next graph, we've got a couple of things going on here. We've got the 1/2 as the base. So in the last video, we showed how a base of 1/2 is an exponential decline. But wait, there's a negative here, right? What did a negative mean when we graphed before? Well, a negative would mean that we would reflect across the x-axis. So let's go ahead and write some of the stuff down. So having 1/2 to the x is this exponential decline like that. Having this negative means a reflection across the x-axis. That just turns it upside down. That's all. You just take this picture right here and flip it over. Now, is there anything inside the function, inside the exponential part? Well, this is just x. There's no plus or minus to this, so there's no shifting left or right. But then you've got plus 7. So plus 7 is out here by itself. It's outside of the influence of the exponent. So it's outside a vertical shift doing exactly what we see. So that's going to be up 7 units. All right, so normally for our exponentials, we have a horizontal asymptote of y equals 0. But now I'm going to shift that up 7. So he's going to have his horizontal asymptote right here. And now, let's see, I'm upside down. So normally, I would have had this. I would have been up here at 0, 1. And with a base of 1/2, I would be doing half of that as I go across this way, and I'd be doubling it as I go backwards. So it would look something like that. That's what it would look like without the negative. But with the negative, it's going to give you a reflection over the x-axis, which for us now, since we've shifted everything, it's going to be a reflection across this horizontal asymptote. So you're going to be down here at 1, and then there's your down 1/2, down 1/4, and so on. But remember, get the correct shape, get the rest of the points. So 1/2 times 2 is 1. 1 times 2 is 2. So you're measuring 2 units from that horizontal asymptote. Double that, you get 4. 4 times 2 is 8. 8 times 2 is 16, which is just going to barely fit for us. And now we just connect the points. But again, before I do that, I want to make sure you understand, you see this pattern. That's 1, 2, 4, 8, and 16. You are multiplying times 2 or dividing by 2, not adding. Okay? And a lot of times students get thrown off, like in the last example that we have right here, and they'll go 1, 2, 4, and then they do 6, 8, 10. You're not adding 2. You are multiplying by 2. 1 times 2, times 2, times 2, times 2. And down here, I'm doing that same multiplication, but that's as I go to the left. Because as I go to the right, I'm dividing by 2. So half of 16 is 8, half of 8 is 4, half of 4 is 2, and so on. But we have to get our key point there first, which is going to be that key point that's 0, 1. Well, I mean, it's negative 1 because I had to reflect across the x-axis. All right, so we just connect the dots, understanding that we have this horizontal asymptote that we are not going to cross. And keep on coming down here. And there we go. So the same graphing techniques that we used a long time ago for graphing our nonlinear functions is still going to work here. It's still going to work for any other function that we come across. As long as we can pay attention to the difference between what's inside versus what's outside, we're going to be okay.